Hi, let's look at the rectangular approximation method as a way to estimate area underneath of a curve. As a quick review, let's take a look at these 4 questions. Take a moment to answer these. Pause the video if you need a little bit more time. Alright, let's take a look at the answers here. For number 1, a train traveling 80 miles per hour for 4 hours will travel a total distance of 320 miles. Number 2, beginning at a standstill, a car maintains a constant acceleration for 5 feet per second squared for 10 seconds. This velocity, after 10 seconds, will now be 50 feet per second. Number 3, a pump working at 100 gallons per minute pumps for 2 hours, or 120 minutes. So, there are 12,000 gallons pumped after 2 hours. And finally, at 8 p.m., a temperature begins to drop at the rate of 1 degree Celsius per hour. 12 hours later, it begins to rise at a rate of 1.5 degrees per hour for 6 hours. The net change in this temperature over the 18-hour period is going to turn out to be 3 degrees. I want to take a little closer look at question number 1 again, the train traveling 80 miles per hour for 4 hours, and I want to draw a graph to represent this. So, a graph that I might use would have a x-axis here, which would be in time, and a y-axis here, which is going to represent the velocity. So here's my velocity, and here's my time, and we have a 4-hour time interval. I'm just going to go from 0 to 4 to represent that. 1, 2, 3, 4, and my velocity is going 80 miles per hour. I'm just going to stick 80 right there. And we know it's a constant rate, so here's the train's velocity over that 4-hour period. Now, we know from answering earlier that the train has traveled 320 miles. The reason I'm drawing the graph here is I want to show a visual representation starting at time of 0 and going all the way to time to 4. Because I have a constant rate of 80, I've got a nice rectangle here, and I can actually find the area of this rectangle as that space underneath the curve, which would be 80 times 4, which we already calculated as 320. And so we've made note here that the area underneath the curve has a relationship to the total distance traveled. Although we realize that most of the time you're not going to have a constant velocity, like if you were driving in a car. So you might have a graph that looks more like this, and your car traveling velocity might do something more like that. And so if you want to know how fast your car is traveling, you would want to find the area underneath this. And so we're going to learn how to estimate what that total area is by doing the rectangular approximation method. So let's start with this question here. Consider the region bounded by these 4 equations: y equals x squared plus 1, y equals 0, x equals 0, and x equals 2. I'm going to graph that out here. X squared plus 1 would be a graph that's a parabola like that. Y equals 0 is a line right on the x-axis. X equals 0 is a vertical line on the y-axis, and here's 1, here's 2. We've got x equals 2 as a vertical line here. Okay? So that's the area that we're going to try to approximate. We're going to do something called the left rectangular approximation, or LRAM, and we're going to use 4 subdivisions to break this down. Okay? So, since I'm going to break 0 to 2 down into 4 subdivisions, the numbers that I'm going to use are intervals of 1/2. 0 to 1/2, 1/2 to 1, 1/2 to 3/2, and 2. So you can see that if I go ahead and separate this, it'll become 4 subdivisions. I'm going to use the left endpoints on these markers to draw the rectangles. So starting at 0, I'm going to draw a line straight up to my graph. I'm going to go straight across to the next marker, which is at 1/2, and you can see how I'm creating a rectangle there. That's my first rectangle. Second rectangle is going to come from 1/2. Go vertical up to your graph at y equals x squared plus 1. Go straight across until I hit my next marker at 1, and there's my next rectangle. My third rectangle is going to be from 1. I'm going to go straight vertical up to y equals x squared plus 1. When I hit my graph there, I'm going to go right across, and then I'm going to come down there at 3/2. So that's my third rectangle. And my fourth rectangle here, go up to the graph, come across. And so you can see we have 4 rectangles there, which if I figure out the areas of each one of these rectangles, it won't be exact, but it will be an estimate of the total area underneath the original curve, y equals x squared plus 1. Now it's going to be an underestimate, as you can see that there is some extra space there that we have not accounted for. Let's calculate this value right now. Each one of these rectangles has a base value here of 0 to 1, right? Or sorry, 0 to 1/2. So each one is 1/2 a unit long, and then we need to figure out the height for each rectangle, which is the height until it hits the y coordinate of the x squared plus 1 equation. So to calculate this and to figure out the approximate area of this problem, I'm going to say the LRAM will have the 4 rectangles of 1/2 times each one of these numbers here. So the first number there from at 0 would have been the value up at 1. Then my next rectangle would have a base of 1/2, and if I plug in 1/2 into the equation, I'm going to have a value of 5/4. Next rectangle had a base of 1/2, and when you plug in 1, you're going to get the value of 2. And the last one there is going to be when you plug in 3/2. So you'll have 1/2 times 3/2 plugged into the equation gives you the answer of 13/4. Since all these have 1/2 involved, I can factor out a 1/2 to make this a little bit easier to calculate, and then I can just do the numbers of 1 plus 5/4 plus 2 plus 13/4, which will end up being a total value, if you add those up and divide by 2 or multiply by the 1/2, you'll get an answer of 15/4. And so that's the approximate area underneath that curve. So that's using the left endpoints. But let's redo this problem again here, and let's look at this equation if we were to look at it doing the right side, or RRAM. Against 4 subdivisions, so here's y equals x squared plus 1, here's 1, here's 2, I'm going to go vertical line here, vertical line at 0, and we still have the y equals 0 equation that bounds us. Alright, again this time I'm going to do 4 subdivisions, they'll still be at 1/2 and 3/2, but this time when I create my rectangles, I'm going to use the right side. So I'm not going to start with 0, but I'm going to start over here at 1/2. And I'm going to go 1/2. I'm going to go straight up. But this time, instead of going to the right, I'm going to go back to the left. And that's my first rectangle. So there's a little bit of extra space this time coming from the right side. I'm going to go to the next one and go to 1. I'm going to go straight up to the coordinate of the where it hits x squared plus 1. I'm going to move over to the left, and I'm going to draw my rectangle down this way. So we're using 1/2, 1, 3/2, and 2. Those are my right endpoints here. That'll give me my 4 rectangles coming from the right side. And you can see here at 2, I move back to 3/2, I come back down, and that's my 4th rectangle. So you can still see there are 4 rectangles, but this time we are going to have an overestimate because we have way more area in the rectangles than was originally in the curve. So let's calculate this one now. the RRAM, there we go, RRAM would have an approximate area. Each one of those bases is still 1/2, but this time my numbers have changed. The first value is no longer the value at 0, but is now at 1/2, which is that value of 5/4 that we had calculated earlier. Next one would be the value at 1, which was 2. The next value would be at the 3/2, which turned out to be 13/4. And the final one this time is going to be 1/2 times the value at 2, which when you plug 2 in, you get the value of 5. Again, you can simplify this by factoring out the 1/2 since they all have the same base length of 1/2. And so you can do 5/4 plus 2 plus 13/4 plus 5. Add up all those numbers, multiply it by that 1/2, and this time we knew it was going to be more. The area we approximate is going to be 23/4. And so that's how much area based off the rectangles we have. So since one was an underestimate and one was an overestimate, you could conclude that somewhere in between should be the actual area underneath y equals x squared plus 1 from 0 to 2. There is one final one that we'll talk about.